Okay, so we're going to take a look at another electromagnetics question. Here we're told a proton is initially moving perpendicular to an electric field. The field has strength 1.5 kilovolts per meter. The proton is initially traveling at a speed of 500 meters per second. We are asked how long does it take before its velocity parallel to the field is equal to its velocity perpendicular to the field, and then we're asked what is its displacement at this time. So there's quite a lot we have to do here. We're going to set up a little diagram. I'm going to choose to orient the field. Let's make the field this way. Let's draw some parallel plates and then draw a field between them. It actually doesn't matter the way we set this up. So we'll make this positives, we'll make this negatives. So in the case where we have a field like this, the standard field lines will go from positive to negative. So we have something along these lines. Now the proton, this is a proton, is initially moving perpendicular to an electric field. So the proton is initially entering it this way. Parallel would be this way, perpendicular is this way. We're told the field has a strength of 1.5 kilovolts per meter. Well, that's 1500 volts per meter. We're told the proton's initial velocity initial is 500 meters per second. 500 meters per second. So how long does it take before its velocity parallel to the field is equal to the velocity perpendicular? Okay, so we're going to set up acceleration, velocity, and position equations. So we have to pick our x and y directions. So we're going to pick up to be y, going to pick across to be x. So we are going to ignore gravity in the case of this question. So this is, you won't do this with every question, but with this question we're just going to ignore gravity to make it a little easier to calculate. So for part A, we have acceleration in x. This will be 0. This particle, we're told, is a proton. So it has a positive charge. That means it's going to move towards the negatives. So it's going to have an acceleration in y, but it has no acceleration in x. So acceleration in x is 0. Acceleration in y is going to be the acceleration from the field, and it's going to be negative because of the way we've set up the equation. So the charge on a proton is 1.6 times 10 to the minus 19 coulombs. So charge for a proton is 1.6 times 10 to the minus 19 coulombs. So the acceleration here will be the charge times the field. So this will be the negative of the charge times the field divided by the mass. We also actually need the mass of a proton in this case. So we'll quickly get this number. Mass of proton. The mass of a proton is about 1.67 times 10 to the minus 27 kilograms. So mass of proton is about 1.67 times 10 to the minus 27 kilograms. 27 kilograms. So we get the acceleration in y is going to be equal to the charge, 1.6, the negative of the charge, 1.6 times 10 to the minus 19, multiplied by the field, which we said was 1500, divided by the mass, which we said was 1.67 times 10 to the minus 27. So this will give us acceleration in x is 0, and it'll give us acceleration y is minus, we've just got to evaluate this expression, 1.6 times 10 to the minus 19 multiplied by 1500 divided by 1.67 times 10 to the minus 27. So I get 1.4371 times 10 to the 11. So we're going to make this 1.44 times 10 to the 11 minus 1.44 times 10 to the 11. Just tremendously large acceleration. So now we need to find the velocities. So this is our accelerations. Velocities. The velocity in x will be the initial velocity in x. the initial velocity in x was 500 meters a second, so this will be 500. The velocity in y will be the initial velocity in y plus the acceleration times time. Initial velocity in y was 0, so this will be minus 1.44 times 10 to the 11 times time. And the positions, we can find these as well. If we let this start at 0, 0, the position in x will be 500 times time, and then the position in y will be minus 1.44 divided by 2 times 10 to the 11 times time squared, plus the starting position in y, well that's 0. So these are our acceleration, velocity, and position equations. Now question A says, how long does it take before its velocity parallel to the field is equal to its velocity perpendicular? This is, when is Vx equal to Vy? So we need to find Vx equals Vy and solve this for time. So we get 500 is equal to minus 1.44 times 10 to the 11 times time. Now we do have to be very careful here. Because we're doing this in quite a crude way, the t value is going to be negative, and we're just going to make that positive, right? Because this is time after. Because we're using Vx is Vy, we're getting some unusual things happening with the signs, but we're essentially just going to ignore this negative for the purpose of finding this t value. So we're going to divide both sides by minus 1.44 times 10 to the 11 minus 1.44 times 10 to the 11. So this tells us that the time is 500 divided by 1.44 times 10 to the power of 11. My calculator tells me this is 3.47 times 10 to the minus 9. 3.4722 ... times 10 to the minus 9. So therefore, the time taken is about 3.47 times 10 to the minus 9 seconds. So it doesn't take very long. Now part B, we're asked, what is its displacement at this time? So now we need to use the position formulas. We need to evaluate these formulas at this time, then do the square root of the sum of squares. So we have the position in x, we'll call this value here t1. Position in x at t1 is going to be equal to 500 times this number. So 500 times 3.47 times 10 to the minus 9 is 1.74 times 10 to the minus 6. 1.74 times 10 to the minus 6. I am rounding these numbers, but that's fine because these are just approximations anyway. And then we have position in y evaluated at time 1 is, this one will be negative, so it will be minus 1.44 divided by 2 times 10 to the power of 11, and then we're going to multiply this by the time value here squared. So this is going to be multiplied by, we have what, 3.47 times 10 to the minus 9 squared. So we're going to get some comically large value here. So it'll be minus 8.67 times 10 to the minus 7. 8.67 times 10 to the minus 7. So we're just approximating these. These are quite crude numbers because of the way the question's working. The question essentially isn't going to find the actual values that you would really get. We're just using some of the topics from here to sort of learn about how we could do this in theory. So these are just crude numbers, but they're approximations. So the position will be the square root of the sum of squares of these. Position will be the square root of px when evaluated at t1 squared plus py. I've written these are both px. Let me fix this up. This one is not px, this is py, because we had x first and then y second in our formulas. So py evaluated at t1 squared. So this tells me the displacement, which I'm going to call p, or the value associated with the position, is the square root of the sum of squares of these two displacements. So we get 1.74 times 10 to the minus 6. And then for the second question, we have 8.67 times 10 to the power of minus 7. So let me just check all of this. Yep. This comes out at 1.944. So let's say this is P is 1.9440 dot 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 times 10 to the minus 6. So therefore, what is the displacement? It's about 1.94 times 10 to the 6 meters. 10 to the minus 6 meters. This is the answer we're after. So this is an incredibly tiny distance. Essentially what's happening is this particle is moving into the field. The field is accelerating it with a tremendous magnitude of acceleration. It's taking barely any time at all in order to gain an incredible amount of velocity in the perpendicular direction. So these velocities are becoming equated incredibly quickly. And because of that, it's not traveling very far, right? It's happening very fast. It's not going very far. This is what we're seeing, and these are the answers to this question.